Okay, so I'm Lu Sicheng, the first year student of Earth Science, and I'm presenting the coursework of GEOL 006, Surface Processes. And my topic is the surface processing and deep soils, deserts, lakes, and islands. Okay, in this presentation, I will explore how surface processes shape contrasting environments across the world. So first, we will look at the three locations: the hyper-arid Namib Desert in Southwest Africa, a tropical atoll in Cook Islands, and a coastal wetlands system of Lake Manzala in Egypt. So these places are influenced by different processes combinations, like alluvial winds, marine currents, and human impacts, and help us understand how sedimentary environments formed and evolved today. And here's a map to show the position of each of the places. The aim of this investigation is to explore how surface processes shape contrasting landscapes. And to do this, I will describe each location's geomorphological and geological setting, identify the dominant processes and depositional environments, and infer the potential sedimentary rock types being formed today. Let's begin with the Namib Desert. Located in Southwest Africa, I've put a GIS picture from Google Earth. So this region is characterized by the vast sand sea and a range of dune types. We see Barchan dunes, which from under unidirectional winds, linear dunes shaped by bidirectional winds regimes, and large star dunes like iconic Big Daddy dunes from under multidirectional winds. Another key feature is salt pans of Soso-Valley, which indicates the intermittent water flow and strong evaporation. Also, there's another dried up salt pans exists on the coast, formed by flooding. Geologically, the area lies on the Precambrian basement overlying bed, the sedimentary cover, and the Namib is one of the oldest and driest deserts in the world, classified as hyper-arid, with minimal rainfall and intense evaporation. The surface processes in Namib Desert are mainly Julian, marine, and evaporative in nature. First, the dominant Julian processes are driven by southeastern trade winds, which transport sand by siltation, creep, and suspension, forming extensive dune fields. These winds are responsible for shaping various dune types and maintained active and transfer across the desert. Based on the direction of land dune, we can infer the direction of trade winds approximately. In coastal areas, marine processes also played a role, particularly through the Benguela Current, a cold upwelling system that influenced sedimentation along Namibia's desert's western shoreline. The interaction produced subhas or coastal salt flats, as seen in the Google Earth image. Finally, under hyper-arid conditions, strong evaporation leads to the formation of evaporized deposits. These processes combine to create a mixed depositional setting. Julian processes domain inland, while marine influence is seen along the high-energy coast, and low-energy conditions promote salt pans formation in enclosed basins. We can infer variety of sedimentary rocks forming. First, widespread dune activity driven by Julian transport suggests the formation of Julian sandstone, which is typically well-sorted and well-rounded due to continuous wind reworking. In some cases, especially with the high quartz contents and minimal feldspar, these sands can become coarse ironites, as shown in this hand-drawn description. Along the coastal line, marine influence by the Benguela Current contributes to the formation of marine sandstone, possibly with more mixed grains types and sedimentary structure influenced by the tidal or wave action. In low-lying interdune and subhas area, evaporized minerals precipitate for saline water under intense evaporation. This includes gypsum, calcrete, and halides. This rock reflect the environments of coastal deserts. The second place, Cook Islands, are located in South Pacific and represent a textbook example of tropical carbonate island system. The landscape is defined by ring-shaped atolls enclosing shallow lagoons with isolated patches of land known as motus, remnants of high volcanic islands. Geologically, these islands lies above a hotspot, where volcanic activity initially from high islands. Over time, this island undergoes subsidence, while coral reefs grow upwards, forming first fringing reefs, then barriers, reefs, and eventually atolls. This central diagram shows the Darwin atoll formation model, a sequence from volcanic islands to fringing reefs, then to barrier reefs, and finally to atoll, as the volcanic core sinks below sea level. In this particular case, although there is a remnant of basalt islands, as you can see on the GIS picture, the presence of a ring-shaped reefs and a submerged central peak suggests we are observing an elevated atoll, not just a barrier reef. Marine processes such as wave action play a major role in shaping the outer reef ring and redistributing carbonate sediments along the lagoon margin. Biogenic processes are dominant within the reef system. Coral polyps and algae contribute to the carbonate production, building up the reef structure and generating fine carbonate mass through the biological breakdown. On the expose of the motus, the small sandy outlets on the reefs, Julian processes can reward carbonate ascents, forming dune-like features. In addition, evaporation is restricted areas of lagoons may lead to the precipitation of evaporites, especially during dry seasons. These combined processes create a carbonate-dominant deposition setting, with three main zones: the reef ring, the shallow protected lagoon, and the motu outlets. The Cook Islands produce a variety of rock types reflecting their volcanic and carbonate origins. The main biogenic product is limestone, formed from the coral and algal remains. Chert may form from siliceous plankton in deeper parts of the lagoon. Gypsum can precipitate the restricted areas, both as an evaporite and from biological activity. Wind-blown carbonate sands on the motu could form minor Julian sandstone. And finally, the underlying basalt represents an original volcanic island core. These rocks recording the transition from volcanic island to major carbonate atoll. Lake Menzala in northeastern Egypt is part of the Nile Delta and shaped by both natural and human influence. Its landscape includes the coastal lagoons, wetlands, marshes, and barrier islands, visible in the satellite imagery. Human modification like dams, drainage, and land accumulations have significantly altered water flow and sedimentation. Geologically, the area sits on the Precambrian basement rock, overlain by fine clastic deposits from the Nile. And it's a wave-dominant delta with longshore drift stripping the coast and the Dimeta branch showing a sinuosity of 1.47. This feature highlights the combined roles of river impulse, marine energy, and human activity in shaping this complex landscape. Lake Menzala's depositional setting results from the wave-river biological and human processes. Wave action causes a longshore drift, forming a barrier island and sandbars. River impulse delivers the fine sediments into a lagoon, creating mudstone deposits. In wetlands, biogenic activity from the peat and organic rich mudstone, often with bioturbation. Human action like damming and land accumulations can reshape the sediment pathways. This creates a mosaic of depositional zones, from high-energy coast to low-energy lagoon and evaporitic flats, making it an textbook hybrid system. Because of the spatial complexity at Lake Menzala, I've outlined the key zone in red to show where different rock types lie from. In barrier and tidal areas, we expect the sandstone, well sorted, shaped by waves and tidal energy. The lagoons favor mudstone and shale, deposit in low-energy, fine-grained condition. In wetlands, organic accumulation can from peat, which may transform into lignite with burial. And in isolated or reclaimed flats, evaporation can precipitate gypsum and other evaporites. Altogether, this lithology represents the diverse depositional environment across this deltatic wetland system. And in summary, all three environments are shaped by multiple surface processes, not just one. Julian and evaporation overlap in desert and atolls, and landscapes clearly reflect these processes, allowing interpretation from the satellite imagery. But they differ in energy, dominance mechanism, and human impacts. From the windy Namib Desert to the biogenic reefs of the Cook Islands and the altered wetlands of the Lake Manzala, understanding this pattern helps us interpret both present environments and their preservation in the rock records. And here's the reference list I used for do this presentation. And these are for your information, and I think that's all. Thank you.